chapter 10, part 1, right? And we're going straight into gases. So we're being asked here, what exactly is a gas? A gas is one of the three states of matter, right? It was the three phases of matter. We talked about solids, we mentioned liquids, and then we mentioned gases. And this chapter does focus on what a gas is and the behavior of gases. So we're told when we're looking at gases at a particular level. Gases are composed of particles that are moving randomly and they're very fast. They tend to move very fast in their containers. So when you have a gas particle, like it shows right here in this image, if you look at the size of the container is huge compared to the size of the individual gas particles. So the gas particles tend to be tiny. They're tiny. And then if you look at the space between the particles, there's a lot of space, right? They tend to be far apart. You have a lot of space. And then because they're tiny, they don't really occupy a lot of space. The idea is if you took all these gas particles and try to figure out what the total volume they occupy in a container, it will be very small, very, very tiny compared to the size of the container. So these are very tiny particles. And you can almost say that they do not take up much space. The density is very low because they're very far apart from each other. We're told that they're moving very fast. Gas particles are very energetic, right? They travel in straight lines. So we're told here gas particles move in straight line. And then when they're traveling, they keep traveling with a high speed or velocity until they collide with each other. But we'll be told later on that their collision is elastic. And so elastic means that when they're colliding, they don't lose energy as a result of that collision. Because remember, in order to have a gas particle or to have a chemical in a gas state, the particles have to be moving very fast. When they slow down, they become liquid. When they slow down even more, they become solids. So gas particles are only gas particles because you're moving very fast. Okay. A gaseous atom or molecule exert a force against the wall or against the other particle when they collide with each other. So when the particle, if we're looking at a cross section and you have, this is either say a wall of a container and you have the gas particle colliding with that wall, in the point of impact, there's a force that's exerted from the particle against that wall. And there's a certain surface where this is happening. And that surface will have an area, right? So we know pressure is equal to force exerted per unit area. So as the particle collides with the wall, it is exerting a pressure. So we're told here molecular collisions or particulate collisions result in the pressure of the gas. So whether it's colliding with the wall, like we see right here of the container, or if it's colliding with other particles, all those collisions are exerting and causing the pressure of the gas. And not only causing it, they're also sustaining it. Okay? Okay, so here we're spending some time defining what pressure is. What exactly is the gas pressure? Pressure is the force exerted per unit area by a gas molecule as it strikes the surfaces around them. So as they collide with the wall of the container, that collision causes pressure and keeps the pressure going. Okay? We're told gas pressure is a result of constant movement of the gas molecules and their collision, because they have to be moving to collide, right, with the surfaces around them. The pressure of the gas depends on several factors, but bottom line, before we get into this part here, bottom line, number of collisions determines the pressure of the gas. So when you're asked to identify what is causing the pressure to go up and down, fundamentally, you want to link the collision to the pressure. If you can find a way to see that the collision is increasing, then you will notice that the pressure is increasing. So years ago, I was studying this, just like you guys. I used to be a student once upon a time. And I was in school learning about the importance of collision and pressure. And then I used to be an athlete. All of these are years ago. And I think it was fall. I don't remember exactly when. I want to say it was fall because the teacher didn't care much about heat. He cared about cold. So during fall, the coach was trying to condition those of us who were in track and cross country. So he had us in the gym run distance. Now, sometimes we run miles in the gym, but sometimes he had us run from wall to wall in the gym. And he would tell us run from one end of the gym. So that would be one end right here. This would be me running all the way to the other end of the gym. And he wanted us to tap the wall or to hit the wall when we got to the wall, right? It wasn't just me. There were a bunch of us students or a bunch of us student athletes running in that gym, and we were all doing the same workout. So as we were running, you'd hear tap as a person got to the wall, you'd hear tap, right? At some point, many of us were just running back and forth, and you just hear it tap, 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 tap. So in my head, you know how creative I like to be, right? I'm thinking this is what the gas molecules must feel like. Of course, gas molecules actually move fast, not like me, right? But as they collide with the walls of the container, that's where the pressure is being generated. So as I'm running and tapping the wall, I'm thinking, man, I'm generating pressure right here, applying that pressure, right? Okay, this is all in my head, y'all, but I'm trying to make sense of what I'm learning in class and trying to relate it to my life. And for me, it made sense. You have to have collision to have pressure. Okay, so not only that, and then we're told here, apparently there's certain factors that influence pressure. So I'm going to give you guys some scenarios and I'll come back and look at this. So I'm going to go off script here and say, these are factors that influence pressure. Okay, so these are factors influencing pressure. Okay, let's start with condition A. In condition A, we have a container of the same size. Okay, you know what? I'm going to be lazy, y'all. How about we call this efficient? I'm going to be efficient and then copy. See, in the class, I cannot copy this. So the container is the same size, right? And then I'm going to put some particles here. 3. And here I'm going to put more particles. 1, 2, 3, 4, 5, 6. Okay? So these particles are gas particles and they're in constant motion. My question to you is this. If the temperature is the same, because I haven't changed that, and the only thing I've changed is the number of particles, which box, let's call this, no, not A or B, let's call this 1 or 2. Which box 1 or 2 will have the higher pressure? I'll give you time to think about it. Box number 2, higher pressure. If you answered this, you are correct. So why are you correct, you ask? I'll tell you why you're correct. We have more particles, right? So you're going to have more collisions. When you have more collisions, what do you have? More pressure. Because remember that the pressure is generated by collisions. So if the collisions are happening, you have more pressure, right? And that's the correlation here. More collisions, more pressure. It kind of reminds me of that commercial, more flags, more fun. That's the Six Flags commercial, right? So of course, how do I hear that? Like regular people? No, I hear that they're almost guaranteeing us if they have more flags, you will have more fun. That's how I heard it, y'all. So what do? I go to Six Flags. Do I have Six Flags level of fun? No, I think at best I had 1 flag. Okay. I just don't like rides. So for me, that wasn't true. But this is not a situation where it's true for some gases and not true for other gases. As long as gases are having collisions, they are generating pressure. Okay. Next one, number B. Y'all, I got to bring in these stories. Where else will I tell these stories? Second one, let's make the container smaller. Let's shrink the container. So the first one will be bigger. The second one will be smaller. And we'll keep the particles the same. So we have 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. Okay. So which one has the higher pressure? The container, I kept the number of particles the same. We've got 7 particles on the left and right. But on the right side, I shrunk the container. So once again, we have smaller space or smaller volume. This will result in greater number of collisions. So why greater number of collisions? Because the particles don't have to travel as far, right? They don't have to travel as far. So I'll say here, particles do not travel far. As a result of that, we do have greater pressure. But it's not because they're not traveling far. We just end up with having more collisions. Remember, you want to tie in whatever argument you have or whatever support you have, you want to ultimately end with more collisions, more pressure. Less collisions, less pressure, right? Okay. C. Oh, we have the same size particles, or not particles, same size container, and same number of particles. But this time, I have to think about what the factors are. But this time, what I changed was the temperature. So I'll make this low temp, and this is high temperature. Okay, so we have low temperature, we have high temperature. With a low temperature, what we notice is the molecules are sluggish. So it's almost like they haven't had their coffee, right? They're sluggish, they're moving slow. On the high temp, they're moving fast, like they just had a cup of coffee. And because of that, when you have a high temperature, you're going to have greater number of collisions. And with more collisions, what do we have? Greater pressure, because more collisions equal more pressure. Okay, so let me go back and review this. The number of gas particles in a given volume will influence the pressure. The volume of the container will influence the pressure. The average speed of the gas particles influence the pressure. So I talked about all of this here. I talked about it differently, but I have covered all that. So I'm going to go ahead and move on. Okay, I mentioned before that the gas pressure is maintained by the collisions of the particles. So here we're looking at the gas pressure and the kinetic theory of gases. So kinetic theory is a theory that talks about the movement and the behaviors that we see in gas particles that are generated by their movement. According to the kinetic theory of gases, collisions of gas particles with each other and or surfaces are said to be elastic. The elastic is illustrated here. So say you have two bowling balls, right? And this is the before, and then this is the after. I'm trying to be cool. After. The idea is when the balls have a certain velocity or certain energy, and then they collide with each other, they don't just stop moving, right? They bounce off and then they move with energy. So this is an example of elastic collision, right? The idea of elastic collision, you essentially have the energy of the balls before and then the energy of the balls after, or the speed of the balls before and the speed of the balls after. The idea here is the balls do not lose energy or slow down as a result of the collision. Or slow down because of collision, Okay. And then we have inelastic collision. So when I was saying this in class today, somebody asked me, does elastic mean that it's stretchy? No, elastic just means that when you, you know what? It doesn't mean it's stretchy, but I think it may mean, I'm not sure, I'm speculating. It just kind of bounces back, right? It hits and then bounces back, kind of like elastic bounces back. You know, when you pull it and let it go, it just goes snaps back. I think that's why they call it elastic versus inelastic, right? I'm speculating. I don't know. Y'all can look into that. But in an inelastic collision, the molecules don't just snap back into their original velocity or energy. When they collide with each other, the way the energy is distributed in the collision, it changes things to where sometimes the particles move together. So if they're moving together, they're heavier, right? So they're not moving at the same speed they had before. Or sometimes the energy transfer during the collision causes some particles to morph in the way they are. And so that changes how they move. The bottom line here is it changes the speed and it changes the energy. So things are not maintained. Things don't just snap back, right? So let's go ahead and move on. I talked about this, the concentration of the particles influencing pressure. I talked about the particles and the volume. And so I will skip over that. The next slide we're looking at here is the pressure unit. You want to be aware of pressure units. Pressure is measured in millimeters of mercury. So we have torr, and as far as torr is concerned, 1 torr is 1 millimeter of mercury, 1 atmosphere is 760 millimeters of mercury, 1 atmosphere is 760 torr. Okay, so Torricelli is the scientist that was studying the pressure and the pressure units. And so he came up with the equality that 1 atmosphere is equal to 760 millimeters of mercury. You want to have this table of pressure units. So this table, this is one of those tables in chemistry where we park over here a little bit and make sense of what we're looking at. This table is a table of equalities. Can you tell from here? Not necessarily, but I'm going to start from the bottom, okay? All of these measurements here are equal to 1 atmosphere. So you want to read it as 1 atmosphere is equal to 101325 pascals, okay? Or you can read it as 1 atmosphere is equal to 14.7 psi. Or you can read it as 1 atmosphere is equal to 760 torr. Or read it as 1 atmosphere. You get the point, right? Am I going to go through all this? No, just the last one. Is equal to 29.92 inches of mercury. Okay. All of these numbers are equal to the atmosphere here on the bottom. So you can use it like that. So you can use these as equalities. Let me erase this. I don't know what I'm doing here, y'all. I know I'm doing something, but it's a struggle. Okay. So now that you know how to use it, let's go ahead and the problem here, the theme is converting between pressure units. Let's see how that plays out. A cyclist inflates her high-performance road bicycle tire to a total pressure of 132 psi. So you have a pressure of 132 psi. That's the given pressure. What is the pressure in millimeters of mercury? Oh, I mentioned this in class and I forgot to mention it here. I mentioned in class that when I was learning chemistry, I used to get lost a lot. Part of the reason was because we were learning chemistry in middle school. My first year of middle school, we were learning the elements in the periodic table. It was more like, what is Na, sodium? So it was more like the ABCs, right? Then at a certain point, the middle of middle school, about halfway through, our middle school is 4 years, so about year 2, we're learning these conversions, and I'm just like, molar conversions. I'm trying to figure out what is going on. But by us learning these very early on in life, it gave us more room to mess up and more room to figure it out. So we got to see the information over and over again. Anyway, back to what I was trying to refer to. When we're doing stoichiometry and molar conversions, while I wasn't really catching on the theme, it took me a while to realize there is a theme. And when the teacher is doing the conversion, there's a rhythm to it, right? There's a pattern. It took me a while to realize it was a pattern because I wasn't being told there is a pattern and you have to notice that. Stuff was just being done and I was lost. And some people were getting it. I'm like, how are they getting it? And they were able to predict where the problem will go. And I'm like, I don't even know what is going on. How are y'all able to predict? Then when I realized there's a pattern, I was like, oh, I got it, right? And so before we'll go from a unit, and then we'll go to moles, and then from moles to another unit. I noticed this pattern over and over again. Once I kind of started getting stoichiometry, I'm like, this, I get it. I get this now. When it came to this chapter, I saw a similar pattern, but this time we're going from unit, whatever the unit is, given unit, and not to moles, but to atmospheres. And then from atmospheres to the other unit. So I was like, wait a minute, I see a pattern here. We're going from unit to atmospheres to unit. Okay, I bring that up because it plays out here. We're going from PSI to atmospheres. And from atmospheres to millimeters of mercury. So you see the pattern there? Okay, if we're doing that, we need to have a conversion for right here and a conversion for right here. So we're working with 132 psi. Let me go ahead and add this here, add page. Okay, So we're working with 132 psi. This is my given, right? My first conversion factor, that's the conversion I'm going to be using, is 1 atmospheres equal, oh, sorry, I didn't state my wanted. Look at me trying to work on this stuff. Millimeters of mercury. So my first conversion is going to be 14.7 psi. You're wondering where I got this from back here. 14.7 psi goes with 1 atmosphere. Okay. And the other one will be 1 atmosphere goes with 760 torr. Because torr is the same thing as millimeters of mercury, because that was Torricelli's experiment. And then we have 1 atmosphere is equal to 760 millimeters of mercury. Okay. So we'll set it up 132 psi, and then our conversions are 14.7 psi, 1 atmosphere, and then over here we have 1 atmosphere, 760 millimeters of mercury. Like we've been doing before, make sure your units match diagonally so you can cancel them out, right? And then whatever is wanted is a unit that remains, millimeters of mercury. Okay. Once you see that rhythm, then it's not as overwhelming. And then remember the rhythm and the pattern that we're learning, it's going to help us navigate through places we haven't been to before. When you encounter a conversion you've never seen before, you'll be like, wait, I may not have seen this conversion, but I know how to do dimension analysis. That's the whole point of this exercise, right? Oh, look at me talking all the way. Let me figure out the math here. Because you see, in lecture, in face-to-face lecture, I'll just ask somebody to work this out, and I'll be standing there talking on the board. But I don't have that here. I have to do my own math. Okay. So my raw number without approximating is 6824, right? But we have 3 sig figs. So it's going to be 6820, right? Let's see what they get. And that's the answer we got. They just chose to write it in scientific notation. Well, I cannot write on it because it's a picture. Anyway, you got to see it. And remember, they use this conversion table to convert. Okay, so that answers that question. The next part we're working on is manometer. The manometer. So the manometer is a device that is able to measure the pressure of trapped gas. So we're told the pressure of gas trapped in a container can be measured with an instrument called manometer. Manometers are U-shaped tubes partially filled with liquid, and the liquid is usually mercury that is connected to a gas sample on one end. So the gas sample isn't just floating up in the air, right? It's actually a gas being synthesized or being made in a container. So here we have a picture showing you where the gas is being made, and I just highlighted a part. So chemical reaction is generating the gas, and then as the gas is being made, the gas travels through the connection between the gas and the manometer. So you have a little neck right here of the flask, and it's connected to the manometer. And in the manometer, you have a liquid. So before the gas was connected, the liquids were at same height. So you have the liquid mercury in the arm. These are called arms of the flask. Before the flask was connected, the liquid mercury should have been at the same height, right? But then once the gas got connected, the gases traveled in here and they pushed down against the right arm, right? And then they push correct, and they push down against the right arm so much so that this right arm is now lower than the left arm, right? I'm talking about the height of the liquid. So we have 3 things actually acting here. The pressure of the gas generated by the particles colliding with the wall of the container. And then because we have a height difference here, the height difference generates a pressure only because of the height difference. Now, this pressure is only present when there is a height difference. And then this, I forgot to mention, is also called an open-end manometer. It's called open-end because one side of the manometer is open to the air. Why is that important? Because the side that's open to the air allows air to rush in from the atmosphere. So the air from the atmosphere now influences this end here and tries to push down on the left arm of the manometer, okay? So in the end, there is going to be a competition established between the pressures of the atmosphere So this is competing with the gas pressure and the pressure of the gas. Okay. The difference in the liquid levels is a measure of the difference between the pressure between the gas and the atmosphere. So the pressure due to height tends to be the difference between the gas pressure and the atmospheric pressure. Okay. For this example, the gas pressure is greater than the atmospheric pressure. Okay. Before we move on, let's see why that's the case. Imagine this was a competition, right? That's how I like to see it. And you had a person here pushing down against this liquid, another person here pushing down against this liquid. And so it was like not really like a tag of war, because tag, I think you're pulling the rope. Let's say this is a push of war. I'm kind of making this stuff up, where you're pushing down on the liquid. So the question is, which person is winning? If they started at the same height right here and they were both here, which person is winning? Obviously the one on the right, because they were able to push down on the liquid and push it down, right? So they are pushing with greater force. Now, the person is not a person, it's actually a gas. The gas is pushing down more on the liquid. So when we're writing the equation, I forgot to mention this. In order to solve these manometer problems, you have to generate the equation yourself. You look at the image, and from the image, you write the equation yourself. So from our picture here, we'll say the P gas is the greater pressure, and that's equal to the smaller pressure, P atmosphere, plus P due to height. Because remember, the P due to height is the difference between the two, right? The pressure due to the height difference tends to add to the lowest, the side that's not winning. Okay, the side that has the higher level. Okay, so let's go ahead and practice this in the worksheet I provided here. In this worksheet, we're going to be working on figuring out our own equations and applying them in the problem. And you see, once you get the equation, the problem becomes so much easier to follow and to solve. We're only going to work on A, B, and C. D is somewhat redundant. So these are all open-end manometers, okay? In the first case here, we have the pressure of the gas, so we'll call this P gas. And then it's an open-end manometer pressure of the atmosphere, okay? And we normally have a pressure due to the height difference, but there's no height difference here. So when we're asking the question, which side is winning? Pressure of gas pushing down on here, pressure of atmosphere pushing down here. The answer is neither, because P gas is equal to P atmosphere based on how the picture looks. Because the height of the liquid in the column, the arms, are the same. We're told, for number one, look at diagram A. The mercury column in diagram A are of equal height, implying the pressures are equal, right? If the pressure of the confined gas is 749 millimeters of mercury, what is the atmospheric pressure? So the pressure of confined gas is 749 millimeters of mercury. That is equal to atmospheric pressure because they're equal to each other. What is pressure due to height difference? 0, because the heights are the same. The heights in the arm is equal. Should I say are equal? I just say height in the arm is equal. You get what I mean, right? The height of the liquid in the arm of the flask or the manometer is equal. Okay. For B, let's get the equation, and then we'll apply it to the problem. So I want to get the equation for B and C first, and then we'll apply it to the problem. Once again, you get the equation based on the picture. So in our picture right here, let's see which is winning. If you zoom in, you see that the gas side is slightly lower than the atmosphere side. Then we got P gas here. So we can say P gas is bigger, is equal to P atmosphere plus P sub H. This is a smaller one, okay? It should be P sub H. This third one here, atmosphere is definitely bigger. So P atmosphere equal pH plus P gas. I don't know why I keep writing it like this pH. It's supposed to be P sub H. I'm writing it like it's a pH, right? Okay. So for the second one, the second question goes with diagram B. In diagram B, we said P gas equal P atmosphere plus P sub H. The last one we said P atmosphere equal P gas plus P sub H. Remember, P sub H always adds to the weaker one. Okay. Okay, let me have my calculator ready. I'm just gonna put in the numbers because it's been a long day and I'm tired. The difference in the heights of the mercury column in diagram B is 17. So we got P sub H as 17 millimeters of mercury. If the atmospheric pressure is 769 millimeters of mercury, what is the pressure of the gas, of the confined gas in millimeters of mercury? Now they can ask you the question in different units, so you just add it up and then convert, right? 769 plus 17, that gives us 786 millimeters of mercury. If they ask for this in atmospheres, of course you'll convert. The difference in the heights of the mercury column is, so this right here is 26 millimeters of mercury in diagram C. I've already gotten this from diagram C. If the pressure confined in the gas is the pressure of combined gas is 741 millimeters of mercury, what is pressure due to the atmosphere or atmospheric pressure? 741 plus 26, and we should have 767 millimeters of mercury. Okay. I won't do the last one because it's the same thing. Okay, now we're moving on to this part right here. So we're going to be looking at the basic properties of gases. In the basic properties of gases, what we're seeing here is that gases have 4 basic properties. They tend to have a pressure. They tend to occupy space, having a volume. They tend to respond to temperature or have a temperature. And then when you're counting the gas particles, we're counting them in moles. Okay? These properties of gases are actually related in a simple gas laws. So we're told here these properties or gases are interrelated, meaning that when one changes, it affects all the others. Okay? But for us to see how this plays out, how changing one affects the others, we're going to be looking at the simple gas laws. And in the simple gas laws, it says it describes the relationship between pairs, like 2 of them. So we investigate 2 properties, right? While keeping the other 2 properties constant. So why are we keeping the other 2 constant? If we change too many things at one time, it's hard to tell what is actually causing the change, right? Because you have too many things going on. So you want to investigate 2 things. For example, you investigate pressure and volume. If you're doing that, you want to keep temperature and moles constant. So we'll see how this plays out, okay? Let's go to the simple gas laws. The simple gas laws, once again, there are many, but we're only going over 3. We have Boyle's law, we have Charles' law, we have Avogadro's law. There is Precious law, there is Gay-Lussac's law, but we're just going over these 3. That's what we go over in this book. So we're just trying to keep it simple. In Boyle's law, we investigate the relationship between pressure and volume. In Charles' law, we investigate volume and temperature. Avogadro's law, we investigate volume and the amount. So I'm going to go straight to Boyle's law. When it comes to Boyle's law, we're looking at Robert Boyle and Robert Hooke, but he's the one that gets, oh, Rob and Rob, Bob and Bob. Nice. Okay, focus. So Robert Boyle, right? It's named, this experiment or the law is named after Robert Boyle. I just call him Boyle. He used a J tube to measure the volume of a sample of gas at different pressures. And he observed that there was an inverse relationship between the volume and the pressure. Hence, an increase in one caused a decrease in the other. So let's see how it plays out here. We're looking at the pressure, right? And the pressure or the size of the container is maintained by this weight. It's not really the size of the container, but the space, the volume of the container where the molecules are moving is maintained by this weight here. So that's all this is here for, okay? So the idea is in the left picture, we have a greater volume, more space for the particles to move around. In the right picture, we have less volume, about half the space, okay? The volume here is 1 liter, the volume here is 0.5, so we have half, right? Let's see what else is changing. So we have less space for the particles to move around. Number of particles, we got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. You've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, the number of particles is constant. I know I wrote over my particles, but how else will I count them if I cannot write on them, right? So let me go ahead and erase this part here. Okay, so what we have is the same number of particles. I mentioned to you guys before, if the particles have less to travel because they have less room, they tend to exert more pressure because there's more collisions. So what we're seeing here is the relationship where if there's half the amount of space, we get twice the amount of pressure because it's like we're getting twice the amount of collisions, right? So what can we say about the law then? Bohr's law states that the volume of a gas is inversely proportional to its pressure. So I'm not going to rewrite that because it's written right here. But what I'm going to do is write a statement. That means that if we decrease the volume, decreasing the volume forces the molecules into a smaller space, but they're still moving around. They didn't become liquids. Not yet. We don't have enough pressure to make it a liquid. So the gas particles collide with the surfaces more often, twice as often, increasing the pressure, not just increasing it, but doubling it. Okay. So we're seeing right here when we have a greater volume, we have less pressure. As you decrease the volume, the pressure increases. Eventually, when we have the lowest volume ever, we have the greatest pressure, right? Because this is the lowest volume. And well, not ever, but it's a lower volume, right? And that corresponds with a pretty great pressure. Very, very great pressure. Okay. So lower volume, greater pressure. Okay. Let's go ahead and move on. So from here, I've talked about this before, and this is a restatement of the law. The pressure of a gas is inversely proportional to its volume when the temperature and the amount of gas are held constant. So, I want to do this pattern. I want to show you guys here, right? As we're looking at the law, I did talk about the graph, which is a curve. So I want to add a page here so I can show you guys. Oh, I didn't mean to show you this part, diving. People who like diving, when they get to the bottom of the ocean, they experience more pressure because of the depth, right? But let's go ahead. I'm going to add a page here and kind of go off script a little bit to show you what I want you guys to be aware of. Okay. You want to be able to state the law, right? Boyle's law. I know it's written there before, but y'all know what I got to do. So Boyle's law, we're looking at 4 properties, right? We're looking at volume, we're looking at pressure, we're looking at number of moles, we're looking at temperature. So we know in this experiment and this law, we're looking at how volume is influenced by pressure. That means we have to keep these 2 here constant. Okay, so we're told, when I was in school, I dubbed this the VIP law. Why the VIP, you wonder? Let me tell you, I was in middle school trying to survive this. I knew at this point, I have bad memory, so I have to find a way to engage with it by making it fun. So VIP just indicates that this is the only law. Well, this is the law in the simple gas laws that has an inverse relationship. That's where the I kind of came in. Anyway, the volume of a fixed amount of gas, of gas, the volume of a fixed amount of gas so fixed amount of gas is the same thing as moles, right? Moles is constant. At constant temperature. Okay, so I just said moles is constant, temperature is constant, is inversely proportional to the pressure. Okay, so all I said here, this is the law, the statement of the law, statement. You want to make sure you know that. Then you want to know the implication of that. That just says that if the volume goes up, the pressure goes down, right? So volume increases, that means we have a decreasing pressure. This is the implication. Implication is kind of like how it plays out. Like when you go to a lab, what should you expect? Okay. And then the next thing you want to be aware of is the expression. I know what I'm writing here. This is the expression of the law, and the expression comes from the statement. In the expression, we're saying V is inversely proportional to P, like that. And then from here, we're going to have the equation. Now, I mentioned to you guys before, it's a theme, it's a rhythm that when you're changing the proportionality sign to an equal sign, you replace it with an equal constant. Okay? Rearrange the equation so the constant is by itself. So we get PV equal constant. And sometimes scientists will casually refer to this as PV equal constant law without saying it's Boyle's law. You need to know this is Boyle's law. And then from here, we say P1V1 equal P2V2. Meaning that since P times V equal constant, it will give you the same number. If you're doing an experiment where you have a certain condition of pressure and volume, and you multiply that out, you will get the same number as when you have a different condition of pressure and corresponding volume, okay? Because these have to be constant. P times V has to be the same number all the time. Okay, let's go ahead and work this out in the problem. I'm going to skip over this page. So we're told here, as you breathe, you inhale by increasing your lung volume. We're looking at a practice problem, Boyle's law. A woman has an initial lung volume, so we have volume 1 of 2.75 liters, which is filled with air at an atmospheric pressure of 1.02. So we have a pressure of 1.02 atmosphere. If she increases her lung volume so the lung volume is increased to 3.25 liters without inhaling any additional air. What is the pressure in her lungs? What is P2? So number of moles is constant. We assume she has no fever, right? Temperature is not changing. Number of moles is not changing because she's not increasing the air. She's not inhaling any additional air. So P2 is what we're looking for. So we know we have P1V1 equal P2V2. We're looking for P2. So divide both sides by V2. And we end up with P2 is equal to P1V1 over V2. And this is going to be equal to, what's P1? 1.02 ATM times, I'm going to need more space. What is V1? 2.75 liters divided by 3.25 liters. Okay, let's do our math. I don't feel like thinking right now, so I'm going to use the calculator. 1.02 times 2.75 divided by 3.25. We get P2 as 0.863 ATM. Okay, that's P2. Let's see what they get down here. This is the answer to the work that I just did. We're going to go ahead and move on from here. Okay, so after finishing Boyle's law, now we're moving over to Charles' law. In Charles' law, we're seeing here that we're looking at the volume and temperature direct relationship. So if we're looking at volume and temperature, that means what we're keeping constant is the other two, right? Number of moles and pressure. Okay, so once again, I'm going to add a page here and move on where we left off. And then I know all this stuff is written here, but I just want to make sure I restate the law. Okay, so the statement of the law, Charles' law, is the volume of a fixed amount of gas. Remember, fixed amount of gas is talking about moles, right? At constant pressure. It's important to state that. Is directly proportional proportional to the absolute temperature. So why are we bringing this absolute? Absolute means measured in Kelvin temperature. If you want to observe this law, let me write the whole word out, temperature. If you want to observe this law play out, right? So the implications are, this is a statement. Remember, this is a statement of the law. The implications is, if you want to observe this law in the lab, to see the increase in volume, you have to increase absolute temperature. Not necessarily to see the increase in volume, but to see a linear increase. So not only do we have an increase, a direct relationship, but we have a linear increase. To see that linear increase, you have to track the absolute temperature. And when the absolute temperature is tracked and it's increased, the volume also increases linearly. So you have a linear relationship. So the increase in volume is a result of increasing the absolute temperature. Okay, what is the expression of the law? Expression, you say volume is proportional to absolute temperature, right? What is the equation from the law? The equation is volume is equal to constant in temperature. So what parts of these are constant? Divide by T, both sides, you get volume over temperature. It's going to be constant. Of course, it's going to be absolute temperature. So we say V1 over T1 equal V2 over T2. And this is the equation that we use to solve for problems. Okay. So we have a problem right here. Look at that. The problem shows up. Everything is here. No issues. When you're working out Charles' law problems, remember, you must always work gas law problems with Kelvin temperatures. Okay. Okay, just when I celebrated that nothing is missing. Oh, I skipped over this part right here. My bad. That was a me problem because I'm about to say, where is the page? A sample of gas has a volume. So volume 1 is 2.80 liters at an unknown temperature. We don't know what temperature 1 is in degrees Celsius. When you submerge the sample in ice water at 0.00 degrees Celsius, its volume will decrease to 2.57 liters. What is the initial temperature in kelvins and then in degrees Celsius? So when you're working this out, you all saw how we did all this stuff here, right? So that I'm not all over the place, let me go ahead and move this, copy, add a page and work this down here. So what happened was when I added the page added in the wrong section. I didn't even notice it. So let me go ahead and add my page right here. Right. So after I went ahead and worked that problem out, they want me to work out the temperature in Kelvin and in Celsius. So what is T1 in degrees Celsius and in Kelvin? Oops, go back. I think I over pasted and in Kelvin. Okay. We'll start with the Kelvin first and then we'll do degrees Celsius. So V1 over T1 equal V2 over T2. We're solving for T1. So we're going to flip both sides. Do you have to do it that way? No. A student taught me this a long time ago and I actually liked it. So T1 over V1 equal T2 over no, I'm going too fast, over V2. Now we want to get T1 by itself. So multiply both sides by V1. And we get T1 is equal to, what is T2? You have to convert this to Kelvin. So at 273, be 273 Kelvin, right? So T2 will be 273 Kelvin. V1 is 2.80 liters. And then V2 is 2.57 liters. Let's go. Oops, I'm writing in the space. I'm looking at my iPad, so I don't realize when what I'm writing is kind of, now you guys can't see it, right? Okay, divided by 2.57. So I get 297.4 Kelvin or minus 273, 24.4 degrees Celsius. Okay, so let's see what they got. Yeah. And we can check our answers, right? Okay, our final relationship here is with Avogadro's law, looking at the volume and the number of moles in the direct relationship. So here what we're seeing is, before I go to the stuff on the bottom, we're seeing a relationship between the volume and the number of moles. We have a linear relationship. As the number of moles increase, the space they need increases also, and it's a linear relationship. So when you double the number of moles, you need double the space, right? Okay. So we're told here, yeah, as the amount of gas increases, that's the implication, the volume increases. So let me go ahead and do the same thing too here for this one. So we're dealing with Avogadro's law. With Avogadro's law, what we're looking at here is the volume of a gas at constant temperature and pressure is directly proportional to the moles. Okay? So volume, oh, no. I forgot. What was the pattern again? The implication. Greater volume can handle more moles. Okay? This is the implication, how it plays out in life or in the lab. And then we have the expression of the law. Expression. That will be volume is proportional to number of moles. And then we have the equation. Equation will be volume is equal to constant number of moles. Then from here, we rearrange and say volume and number of moles is equal to constant. And then from here, we say volume 1 over number of moles 1 equal volume 2 over number of moles 2, right? And we have that right there. Great. Now we're going to go ahead and move on and see how this plays out. So we have a problem here. A male athlete in a kinesiology research study has a lung volume of, so we now have number of moles, volume first, equal 6.15 liters during deep inhalation. At this volume, his lungs contain, so V1, right? Number of moles, 1.254 moles of air. During exhalation, his lung volume decreases to 2.55 liters. How many moles of gas does the athlete exhale during exhalation? So they're asking you the number of moles of gas exhaled, not how many moles of gas does the athlete have after exhaling. But we need to find N2 first, right? What they're really asking for is delta N. Delta N will be N1 minus N2, okay? So I'm going to take this information here, copy it over, and then open a new page. Once again, I know it's written on here, but I want to make sure I'm adding a page and writing it there so you all see how it plays out. Okay, so we're doing volume, oops, no, not that. Click on this right thing here. Volume 1 over number of moles 1 equal volume 2 over number of moles 2. We're looking for number of moles 2, so let's go ahead and flip this over. N1 over V1 equal N2 over V2, and then multiply by V2 to get V2 over here, right? So N2 is equal to, what is V2? 2.55 liters, right? And 0.254 moles over 6.15 liters. So let's go ahead and work this out and see how it plays out. 2.55 times 0.254 divided by 6.15. Okay, so I end up with number of moles and 2 being 0.105 moles. Okay, so delta N, which is the amount of moles exhaled, would be the original amount, which was what? 0.254. 0.254 moles minus 0.105 moles. So what we have is 0.14. Did I type the right thing? 9 moles. That's the change in number of moles. Let's see what they get. Oh yeah, 0.149 moles. Great. Okay, so here we're seeing a remix, what I like to call a remix. We're putting all of the pieces together to make one whole, right? So I want to show you once again how they got to this part. So I'm going to kind of add the page right here. And then, of course, this page here will be confirming what we just saw. Okay. So I want to introduce the combined gas law before we talk about the ideal gas law. So combined gas law. In the combined gas law, what we're doing here is then looking at that volume is inversely proportional to pressure. That was Boyle's law. And then we have volume that's directly proportional to absolute temperature. That was Charles' law, directly proportional to temperature, Charles' law. And then we have volume directly proportional to number of moles. That was Avogadro's law. So when you consolidate these, you get volume proportional to number of moles temperature over pressure. Okay. Now, like we saw before, we can replace this with the equal sign and a constant, which is NT over P. And then we can bring all these over to make a constant. So PV over NT equal constant. Now, though I'm showing you this one right here like that, the combined gas law sometimes leaves the moles out. I'm like, I don't know why they leave the moles out, but I'm going to include the moles in there. So pressure 1, volume 1 over number of moles 1, temperature 1, equal pressure 2, volume 2 over number of moles 2, temperature 2. Many books leave the number of moles out in the combined gas law because I guess most problems don't have number of moles in them. And this is what it reads like that. So the reason why this is called the combined gas law, you can see that I'm going to highlight this. The yellow part, the orange part, I selected yellow, but it came out orange. This will be Boyle's law, so I'm going to put B here for Boyle's law. Hopefully you can see that. And then the highlight, the green part will be Charles' law. Now, we don't have number of moles here, but I want to bring the number of moles back in here. So number of moles here, that will be Avogadro's law. And that will be Avogadro's law, right? And so, of course, this would be Avogadro's law right here. This is going to be Charles' law. We don't do Pressure's law, but Pressure's law will be in here. So this combined gas laws, like it says, combines a lot of gas laws. Okay. Now, if we go back here and do volume equal, in the place of C, we put R, which is the symbol for the molar gas constant, and T over P. We can actually multiply both sides by P, and we get the ideal gas law, PV equal nRT. Chemists casually call this perv nerd. The first time I heard this, I was like, the perv, what? It's perv nerd, not pervert, okay? I don't know why they have to make a word from this. Why can't we just read it as is, PV equal nRT? But they say it a lot, they get tired of saying it, so they call it perv nerd. And this is the ideal gas equation. So it's called the ideal gas. Oh, come on. Gas. Okay, I think I pressed something. Ideal gas equation. It's right here. The ideal gas equation, ideal gas law. And in this ideal gas equation, let's start with the value of R. This is where we're defining the terms, right? The value of R is, this is the molar gas constant. This is the ideal gas law constant. And this is the value. Is there only one value of R? No, there's more than one value of R. When I was in school, I learned so many values of R. I was getting confused because I was like, In other constants, if you have a letter that goes with a constant, the letter tends to represent one value, one number, one letter. But in this section here, there's so many different values of R, and you have to know what value of which R to use. Ouch, I hurt myself. Okay, if you're dealing with gas, pressure of a gas, then you need atmospheres because atmosphere goes with pressure. The other value of R is 8.314 joules per mole. Okay, if you're dealing with something that has to do with energy and there is no gas, well, you're dealing with energy, then you want to go with this value of R because there is joules. Does that make sense? Hopefully that makes sense. If it doesn't, just know for this section, the value of R is this value here. Okay, so why do I bring up the value of R? And I skip everything and go straight to the R. I mentioned this to you in chemistry when we started chemistry, this class. I want to review it again. When you have a constant, the constant tends to combine a lot of units, right? Constants tend to, this was my observation, that constants tend to have a conglomerate, many units together. So it does help. It behooves you. That means it helps you if you convert the other units in the same equation to the unit in the constant. What do I mean by that? Look at this constant right here. The number has all 4 units. That means you want to make the volume liters. You want to make the pressure atmosphere. You want to make the moles in moles. You want to make the temperature Kelvin. Okay, so let's zoom and see what they said. Where pressure is atmospheres. Maybe they were thinking what we were thinking. Volume is in liters. Number of moles is in moles. And temperature is in Kelvin. Once again, this is one of those patterns I saw in chemistry after doing it over and over and over again, because at first I wasn't seeing the pattern, right? So you want to do that, not just in this section, in all sections. Okay. Even in the ideal gas law, you can actually generate the other gas laws from the ideal gas law.